So, have you ever stopped to think about how we got from watching an apple fall from a tree to predicting the exact orbits of planets? And then from there to peering into the wild world of quantum mechanics? Well, it wasn't one single eureka moment. It was more like a series of incredible upgrades to the physics we use to describe motion itself. Let's dive into that journey.
I mean, this is one of the biggest questions we can ask, right? How does the universe actually work? What are the basic laws that everything, from a baseball to a black hole, has to obey? This single question has kept some of the smartest people in history up at night for centuries.
And the answers they came up with gave us three totally different, totally revolutionary toolkits. You can seriously think of them like software updates for our understanding of reality. Each new version was a little more abstract, yeah, but way more powerful, and it could solve problems the old version just couldn't touch. So let's walk through these upgrades, one by one. Okay, our first big upgrade, our Physics 1.0, comes from the one and only Isaac Newton. What he gave us was this beautiful, intuitive picture of the universe as, well, a giant clockwork machine. A world of simple pushes and pulls of cause and effect, all ticking along according to a few simple, elegant rules.
Now, to even talk about this clockwork universe, Newton had to invent the language. And the most basic word in that language is the vector. A vector is really just an arrow. It tells you two things you need to know: how much of something there is and which way it's going. So a force isn't just a push, it's a push in a certain direction. Every single movement, every force, it can all be drawn as one of these simple arrows. And this right here, is the engine that makes the whole Newtonian universe run. His second law. It's so simple but so profound. It creates a direct, undeniable link between a cause, the force you apply, and its effect, the acceleration the object experiences. You push something, and this little equation tells you exactly how it's going to move. It's direct, it's powerful, and man, does it work.
And just how powerful is it? Well, with this toolkit, Newton was able to write down the law for gravity itself. He showed that the gravitational pull between any two objects, say the Earth and the Sun, gets weaker based on the square of the distance between them. This wasn't just a rule for apples, it was a rule for the entire universe. And this is where the magic really happens. Using his laws, Newton proved that this specific inverse square force would make planets move in ellipses, which is exactly what astronomers had been observing for years but couldn't explain. It's hard to wrap your head around what a huge deal this was. He connected a simple math equation to the grand dance of the cosmos. Just astonishing.
But as great as Newton's method was, it had its limits. It started to break down with more complex problems. So it's time for our next big upgrade. We're going to shift our thinking away from forces and vectors to a more abstract and way more efficient way of looking at the world, through energy. Welcome to the Lagrangian formulation.
So, what's the problem with Newton's approach? Well, picture this: a little bead sliding along a curvy, twisted wire. If you use Newton's laws, you have to calculate every single tiny push and pull that the wire exerts on that bead at every single moment. It is an absolute nightmare. The math just gets completely bogged down in all these little details. There had to be a better way, right?
And that better way comes from changing the heroes of our story. Forget about force and acceleration for a minute. Now let's focus on two different things. Kinetic energy, that's the energy something has because it's moving, and potential energy, which is the stored energy it has just because of where it is, like a bowling ball held up high, just waiting to drop.
Okay, now this is where it gets really, really cool. A physicist named Lagrange figured out that you can ignore all those messy forces. Instead, you just have to look at one simple value: the difference between the kinetic energy of motion and the potential stored energy. This single number, which we call the Lagrangian, is like a secret key. If you can figure out the Lagrangian for a system, you can predict its entire future without ever calculating one of those complicated forces.
So how does this magic key work? It works because of a deep fundamental idea called the principle of least action. It basically says that nature is, well, kind of lazy in the smartest way possible. To get from point A to point B, an object will always choose the path that costs the least amount of action, which is a value you get from the Lagrangian. Think about a skier going down a mountain. They aren't doing calculus in their head. Their body just naturally finds the most efficient line down, the path of least resistance. That's the path of least action.
All right, we've gone from forces to energy. I mean, how much more abstract can you get? Well, buckle up, because we're about to install the final, most powerful upgrade in all of classical physics: Hamiltonian Mechanics. This isn't just about finding the one best path. It's about seeing the entire map of every possible path, all at once.
This is the absolutely mind-bending question that a physicist named Hamilton asked. He thought, why are we following this one little particle on its single journey through time? What if we could create a grand map that shows every single possible state the system could ever be in, past, present, and future, all laid out at the same time? And the map he imagined is called phase space. Now, this is a pretty abstract idea, so stick with me. It's not a map of physical places, like a map of a city. It's a map of every possible state. A single dot on this map tells you everything, the object's exact position and its exact momentum. One single point tells you the whole story at that instant. And as the system evolves, it just traces out a smooth, predictable line across this incredible map.
So let's just compare these ideas for a second. The old Newtonian and Lagrangian way of thinking is like following one single car with a GPS, watching its dot move along one road. The Hamiltonian view is like zooming out to see the entire roadmap of the country, with every highway, every side street, and every possible destination visible all at once. It's a completely different level of understanding.
And taking this God's eye view gives us these stunningly beautiful and symmetric equations. Now don't get hung up on the symbols here, just look at the pattern. The top one says how your position changes depends on your momentum. The bottom one says how your momentum changes depends on your position. See that? It's a perfect, elegant, two-way street. And that symmetry isn't just pretty to look at. It showed physicists a deep, hidden structure in the laws of the universe that they had never seen before.
So, forces, then energy, then this abstract phase space. Why does any of this matter? Why go through all these increasingly weird upgrades? Because, and this is the crucial part, this whole journey was accidentally paving the road to the biggest revolution in the history of physics.
You can see it right here on the timeline. Each one of these ideas built on the last one, taking us to a higher and higher level of abstraction. Newton gave us the solid foundation, Lagrange gave us a much more efficient engine to run on it, but it was Hamilton who gave us the high-level programming language that was absolutely essential for what came next.
And here it is, the ultimate payoff. The source material says it perfectly. The language that Lagrange and Hamilton developed, this abstract world of energy landscapes and phase space, it turned out to be the only language that could describe quantum mechanics. You just couldn't describe the weird, fuzzy world of subatomic particles using Newton's simple pushes and pulls. It wouldn't work.
And that brings us to the big takeaway from this whole thing. With each step we took away from our simple, everyday intuition about how things move, the deeper and more powerful our description of reality became. The more abstract physics got, the more it could explain. In physics, it turns out, abstraction is power.
So that leaves us with one last really fascinating thought. We've seen that the universe, from the biggest galaxies down to the smallest particles, seems to play by these incredibly elegant rules of efficiency and symmetry. If these deep principles can describe the whole cosmos, you have to wonder, what other complex systems, maybe in biology or in economics or even in our own lives, are also governed by similar elegant rules, just waiting for us to find the right level of abstraction to finally see them?